All right, well, at this time, we've already had a little bit of time to look over your homework. Your proctor should have gone over, it looked like 8 through 12 or so with you from the homework, and you should have just gone over some terminology in this new chapter. We're looking at 24.2, and the topic is electric generators. And so what I would do at this point, if you're watching this from home, or whether or not you're watching this in the classroom, there's an important video that we actually watched in class on Tuesday. And that particular one, sorry, Monday we watched that, and so you would actually be benefited to watch that video either again or faster, but there's a very helpful animation in that video that will help you understand motors and generators much better. And again, I don't have the ability to animate, but I'll try to describe some of those things, but I am actually going to put a link in the description below this video so that you can go from this video to the other one. It's another channel, but it does have a very helpful explanation of, first of all, how current flows through a generator, also how what the whole point of a copper loop is, lines of flux, the visual representation, really everything. And so I'll try to get it all covered in this video, but maybe even watching that after this video would be helpful. But I would pause the video at this time and go watch that. All right, hopefully you got from that video as much information as you possibly could on how generators and motors work. My main goal after you've watched that video and taken some time is to really help you enforce the knowledge of the parts of a generator and a motor. And so we'll start with, first of all, an AC generator. You'll notice that we're talking about electrical generators in general, but specifically this slide will deal with an AC generator. So what's the purpose of a generator? Notice the word generate is to produce. This is a device that produces current. Current is the flow of charges through a wire or a conductor by electromagnetic induction. Remember, electromagnetic induction was the concept that was discovered by Michael Faraday and Henry as they were doing their experiments, when you would take a magnet through a loop of a conductor, and if you change the amount of flux linkage, you could produce a small amount of current. And so a device that produces that current by this electromagnetic induction, or that induced EMF. Well, it's going to have some parts. All motors should have some parts to them, but this specific one, the AC generator, is going to have these 3 parts. Yeah, I'll go through these 3 just real quickly. It's going to have an armature. Okay, an armature, which is a conducting loop, a slip ring. I'll talk more about that. It produces that alternating current, and then brushes. The brushes are important. You'll notice this in most actually, this will be true of AC generators as well as DC generators, but it's really the slip ring that is unique to a AC generator. All right, so you have an armature, a slip ring, and brushes. Now, at this point, we don't know what those look like, so I'm going to go to the picture now. Remember that when we're talking about a motor, you first of all need to have, let's see if I got my writing utensil going here, you have to have flux linkage or magnetic flux. These are B field lines that are being produced from one end of a magnet to another. By the way, they call this magnet that surrounds this coil a field magnet. It's very large and it surrounds it. Most motors have a magnetic property we can talk about in a little bit. But it has those magnetic field lines, and so that's what you'll notice. Inside of the magnetic field lines, you have what is called the armature. The armature is, and I'm using red, so I'll actually start on the blue side. You'll notice it comes out this way, it goes around, and makes a conducting loop. This is the thing that will carry the current through it. So you're talking about Q+, and it is being produced in a certain direction. Obviously, we don't know the direction necessarily because it depends. As it stands, there is no current being produced in this loop because, remember, current is only being produced when something is moving and changing flux linkage. Remember, I was talking through this example with you. If you have a conducting loop, something like this, and you have a number of flux lines that are being produced. Okay, this one particularly has 9. If you take a conductor and you move that conductor back and forth, you can change the amount of flux lines that you cut. And so in this position, you got 6. If you move this over, now you have 9 flux linkages. If you over here, you have 3, and you're changing them because, remember, EMF, induced EMF, is actually found by changing the amount of flux linkage in a certain amount of time. So you will create an electromotive force, which will cause that current to move. And so no electromotive force will exist until you move something. And so you do have to, it would be incredibly inefficient for you to sit here and wiggle a wire back and forth over this. And so what they decided to do was to convert motion as best they can into something that we could use. And so what they did was they determined that we could actually just take this thing and rotate it around an axis. Whether by gasoline, if you're thinking about generators, you pour some gasoline in and it starts to spin. But basically the motion is going to be very helpful. Now I think I have a picture in this slide that might be helpful. Yeah, this one actually is. And you'll notice that as we draw flux lines, there is actually a rotation. This thing is being rotated around. And so notice in this position, notice when it's going something like this through the wire, as it starts to rotate, it'll start to allow more or less, depending on the angle at which this armature is moved, flux lines through it, flux linkages. And so you'll notice right here it cuts through all three of these flux linkages. Over here, none of them are changing, but the whole point of this is that the number of Webers or flux linkages are changing over and over. If they do, you are going to produce current. So it's actually easier to make a loop of wires to do that. And so going back to here, we need to know our three parts. The first one is going to be the armature, and that's simply the conducting loop. It's the main portion. And by the way, this is the simplest armature you can draw. Many times they actually have several loops, and so drawing this kind of to scale, something that kind of goes underneath, you might get something like this, and there'd be another loop, and then maybe one that comes kind of out of the screen here, and you get as many loops as possible, kind of something going on this side, and even one that goes up and in on this side. And so the more lines you could possibly get, the better. But again, we're trying to make this simple. And so in our book, we're making this as simple as possible. So the first part of a generator is going to be this part called the armature. That's the conducting loop. That's the red and blue thing you see there. Number two is going to be the slip rings. Okay? And the slip rings are important because as they move through, you'll notice this red wire contacts the slip ring at each point. And then you'll notice if they connected just to the wires would twist and they'd get all tangled, but these slip rings are able to move with the conductor, and you'll notice this blue wire is attached to this slip ring, and so this is what's going to happen. So basically the gist of it is you've got a current of electrons that is moving like this, but every half rotation or so the electrons actually change directions. Okay? And because of that, you need these slip rings. You're producing, by the way, alternating current. The current actually goes in multiple different ways, and so you're making an alternating current, hence the term AC. And then number three, the main portion here is the brush. The brush is really important because it allows the slip ring to make contact with the conductor, by the way, going to something, maybe a light bulb or something that's going to turn on. But the whole point of this is that this thing is continuing to power something the entire time. Well, again, those are the main portions or important components of a generator. So I'm going back. Here are the three things. You've got an armature, you have a slip ring, you have the brushes. Notice the brushes provide a connection between the armature and the outside wires without letting them be tangled. After that, you have AC, or alternating current. Current changes direction through the conducting loop, and so alternating current will change back and forth, whereas direct would go forward. All right. Again, another helpful picture here. You've got your slip rings. You definitely want to know what those are. These little boxes are called brushes. And because of the slip rings, you're going to produce alternating current every half rotation. And you will get, if you actually take this and you put the phase, you'll get something like this, which is sinusoidal. Notice the position of the actual armature in this bottom image. And that's really all that is going on. Now, again, I'm trying to keep this at the simplest level. Going on to DC generators, we still have our main portions. DC current always flows in the same direction. And the unique thing is that a DC generator actually has, the other one had what was called a slip ring, and so your loop came in, one of them touched here, one of them touched the other slip ring, but the commutator is what we call a split ring. And so what happens is you've got a coil that's touching this one, a coil that is touching this one, and these two continue to only touch one portion of the ring at a time instead of this being one connected, unified whole. And so the commutator is the thing that basically makes DC current possible. It keeps it from making an alternating current every half rotation. And so the commutator is helpful. You can think of kind of the commutative property from math. 3 plus 5 is equal to 5 plus 3. So instead of using AC or alternating current, we're actually able to flip it around so that it continues to go in the same direction. So when you make your conducting loop, you have something like this, and your arrows are going like so. As they start to rotate, they would normally turn, but because of your commutator, it continues to stay in the particular direction it's going. And so that's very helpful. So notice that it has a split ring. That's important. That split ring is called the commutator. It's not a slip ring. Slip rings are part of an AC generator. And so that allows current to always flow in the same direction because of what's called a double switcheroo. And so if you need something to help, kind of a memory device, I don't know if you are a Looney Tunes fan or anything, but back in the day we used to watch, Wile E. Coyote, and of course Wile E. Coyote would always try to get the Roadrunner, and so he would run inside of a log, he'd run out and he'd do his thing where he stands, over a canyon, and he's floating in air. He's just floating there. He looks and he decides he wants to run back into the log, but while he runs back into the log, Roadrunner comes in and he rotates the entire log, and Wile E. Coyote comes right back out, stands here, and he falls. Okay, because of this double switcheroo. It's the same concept. The commutator is like a log that is able to switch that around so that basically current is always going the same direction no matter how it wants to move. All right, so notice the two generators that are produced here. You have an AC generator. Notice the slip rings, the armature coil, you have your brushes. Over here you have the split ring or commutator, that's the term. Commutator, we have the same armature coil and then the brushes as well to keep this working. So those are the three main components. They're a little bit different for a DC generator. You're going to have this commutator. All right, now this particular one is broken, so if I can fix this, I don't know that I can, so I'm going to try to pause the recording, and then I want to resume the recording. So I think I got that right, but basically there are some complex generators out there. One of the things Michael Faraday did say was that it was the relative motion of a coil that made induction. So you could take a coil of wire, you could take a bar magnet, and you could try to put that magnet into the coil of wire, and you would produce in a galvanometer over here a needle that would swing either to the left or to the right based on the actual movement of the bar magnet into the induced coil. Now, the cool thing about that is it actually could just be the wire that you move. It doesn't matter. It's the relative motion of either of them that are cutting the flux linkages. So there are some specific terms that could be in more complex generators, and those specific ones would be exciters, rotors, stators, and the prime mover. I want to go through each one of these just for a brief moment. It mentions in your book on page 367, nope, not 367, I'm much further down the way. I'm on page 369, talks about these important parts. And so the exciter, most AC generators use an electromagnet that gets its current from a small DC generator called an exciter. And so sometimes you need to have an electromagnet and it needs to be powered. And so they use what's called an exciter. Think about it like a spark plug, something like that, that is going to power this thing. The next one is what's called a rotor and a stator. Those two don't go anywhere without each other. And so I wanted to go to this picture so you see them. Usually, stator is a set of, going back to this, rotating magnets that are inside the armature, and the stator is a stationary armature. So here's what we're saying. Now, the stator, okay, let me go back. I'm going back and forth for a reason. Stator is stationary, rotor rotates. That would be the idea. And so what happens is you take the rotor and you put it inside of the stator, so it's coming out like this, and it's rotating. No one said you had to move. This particular one, the rotor is moving. You're moving them relative to each other. And so this one is actually better because now we don't have to move the conducting loop. And so you've got this thing that's spinning around inside of here that's producing the generation of current. And so complex generators may use that. I'm trying to erase this. Okay. So going back, then there's this last portion, and this is what's called the prime mover. Prime means first. It's the thing that causes all the motion. So if you power a generator or even a lawnmower or anything that produces current, you're going to have to use what's called a prime mover. So it's going to be a belt, something. You've got the picture on page 369 of the rotor and the stator. You'll notice that the rotor moves the stator is stationary. The magnet moves inside of the coil, basically, is what I'm trying to say. And then the prime mover is simply like a serpentine belt in a car, something that's going to move that thing. If you know anything about alternators in your car, the alternator is basically it's a generator. It produces current that, as your battery in your car uses current, the alternator recharges the battery based on what you use. So if your alternator goes bad, your battery will go bad quickly. And so it has to be moved by the serpentine belt that also runs your water pump and all the parts of your engine. All right, so that's a complex generator. And then, oh, by the way, these Mac Daddy generators, this is the rotor and the stator. And so you'll see that rotor in the middle, stator on the outside. These get quite large, and this is kind of how most generators work. I'll give you an opportunity on your own time to look at three-phase current. But for sake of time, basically the point is to put as many loops as possible so that with AC current you never have downtime. The simple one loop isn't good enough, and so you'll notice on 369 the three-phase current. I'm going to allow at this time your proctor to assign the homework, and I will see you in the next lesson.